The Crucible of Optimization, Real-World Algorithm Efficiency Chronicles in the ever-evolving landscape of software development. Few topics command as much attention yet remain as misunderstood as algorithm efficiency. This article delves beyond theoretical discussions, exploring real-world scenarios where optimization has made tangible differences, from search engine indexing to autonomous vehicle routing. Understanding algorithm efficiency isn't merely an academic pursuit. It's the backbone of scalable applications that power modern technology infrastructures. By examining case studies from diverse domains, we uncover how subtle improvements in time complexity can yield massive performance gains when scaled across millions of operations. The Big O paradox. When theory meets practice, theoretical analysis using Big O notation often creates a false sense of security among developers. While O(n) algorithms are generally preferred over O(n) superscript 2, real-world implementations frequently reveal unexpected bottlenecks hidden beneath the asymptotic abstraction. A notable example comes from social media platform XYZ Corp. Their initial implementation used a simple nested loop approach for friend suggestion matching, resulting in O(n) superscript 2 complexity. Despite passing all unit tests, production performance suffered during peak hours with user bases exceeding 1 million active users. This led to the adoption of a hash table-based solution that reduced the average case time complexity to O(1). However, implementing this change required rewriting substantial portions of their recommendation engine codebase, highlighting the trade-off between theoretical elegance and practical maintainability. 3 critical lessons emerged. Big O is necessary but insufficient. Actual performance depends heavily on constants, hardware specifics, and input distributions. Caching strategies matter immensely. Proper use of memoization techniques can dramatically reduce effective runtime even within the same complexity class. Profiling beats guessing. Modern profiling tools can identify actual performance hotspots rather than relying solely on theoretical predictions. Redefining search. How Google transformed information retrieval. No discussion of algorithmic efficiency would be complete without addressing Google's revolutionary PageRank algorithm. This breakthrough demonstrated how algorithmic innovations could fundamentally reshape industries while maintaining computational feasibility at scale. The original PageRank model operated by treating web pages as nodes in a directed graph, calculating each node's importance based on incoming links. This approach had an inherent O(n) complexity relative to the number of web pages, which was crucial for processing billions of documents efficiently. By leveraging distributed computing frameworks and optimizing matrix multiplication operations through sparse representation, Google achieved remarkable scalability. Their implementation also incorporated numerous heuristics to prune less relevant nodes before full calculation, preventing unnecessary computation. Further refinements came with the introduction of personalized ranking factors, allowing different weightings based on user behavior patterns while still maintaining overall linear complexity. These enhancements collectively enabled real-time query processing capabilities that were previously thought impossible at such scales. Autonomous navigation, balancing precision and performance. The field of autonomous vehicles presents fascinating challenges in algorithm design, particularly regarding pathfinding and obstacle avoidance systems. Here, algorithm efficiency directly impacts safety and responsiveness in life-critical situations. Consider Tesla's autopilot system, which employs advanced decision-making algorithms running in real time. The core challenge lies in balancing the need for ultra-low latency responses against the requirement for highly accurate perception models. Tesla engineers have developed custom neural network architectures optimized specifically for automotive use cases. Through extensive pruning and quantization techniques, they've managed to run complex AI models on specialized hardware while keeping inference times below 5 milliseconds, a critical threshold for safe operation. Additionally, route planning algorithms utilize hierarchical approaches, combining global pathfinders with local reactive planners. This multi-tiered strategy ensures both long-term optimality and immediate adaptability to changing conditions, achieving impressive results in real-world testing environments. Data compression revolution. Squeezing more out of less efficient data compression algorithms form another cornerstone of modern computing infrastructure. From video streaming services to cloud storage solutions, these algorithms enable unprecedented levels of information density while minimizing resource consumption. Huffman coding represents a classic example of entropy-based compression techniques. Its effectiveness relies on variable length encoding schemes where more frequent symbols receive shorter codes. Despite being decades old, Huffman remains integral to many modern compression standards due to its simplicity and robustness. LZ77 and LZ78 families introduced dictionary-based compression methods that revolutionized file storage capabilities. These approaches achieve better compression ratios by identifying repeated patterns and storing them once in a reference table, referencing them instead of retransmitting redundant data. Modern extensions like Standard combine elements from various methodologies, offering exceptional compression/decompression speeds while maintaining high compression rates. Such advancements highlight the continuous evolution of algorithm design driven by practical needs. E-commerce optimization. Transforming online retail. The e-commerce sector provides compelling examples of algorithmic efficiency impacting business outcomes directly. Consider Amazon's recommendation engines, which process vast amounts of transactional data daily to provide tailored shopping experiences. These systems employ collaborative filtering algorithms enhanced with deep learning techniques. By analyzing purchase histories and browsing behaviors across hundreds of millions of transactions, they generate recommendations that significantly boost conversion rates and customer engagement. Behind the scenes, sophisticated caching mechanisms ensure these computations happen rapidly enough to support real-time interactions. Distributed computing frameworks handle the immense processing requirements, allowing seamless scaling during peak shopping seasons. Furthermore, inventory management systems use predictive analytics powered by efficient forecasting algorithms. These help optimize warehouse operations, reducing holding costs while ensuring product availability meets demand fluctuations effectively. Healthcare informatics, saving lives through computation. Medical fields represent some of the most impactful applications of algorithmic efficiency. In diagnostics and treatment planning, every millisecond saved can translate into improved patient outcomes. MRI image reconstruction processes benefit greatly from fast Fourier transform optimizations. Traditional methods required lengthy scanning periods, but accelerated versions now allow clinicians to obtain diagnostic quality images in minutes rather than hours. Predictive modeling for disease outbreaks uses spatiotemporal clustering algorithms to detect emerging patterns early. These models analyze vast datasets from multiple sources, including electronic health records and environmental sensors, to predict potential outbreak zones accurately. Personalized medicine initiatives leverage genetic sequencing data processed through parallelizable algorithms. Efficiently handling terabytes of genomic information enables targeted therapies that consider individual biological variations, leading to more effective treatments. Financial services, powering high-frequency trading. High-frequency trading, HFT, exemplifies extreme demands placed on algorithmic efficiency. Microsecond-level latencies determine profitability in markets worth trillions of dollars annually. Trading firms invest heavily in low-latency networking equipment and colocation services to minimize transmission delays. However, equally important is the algorithmic efficiency of order execution logic itself. Quantitative analysts develop proprietary algorithms capable of executing trades in nanoseconds, utilizing mathematical models that account for market microstructure complexities. These algorithms constantly evolve to stay ahead of competitors while navigating regulatory constraints. Machine learning models trained on historical price data further enhance trading decisions. Feature selection techniques ensure only the most informative variables influence prediction accuracy, preventing overfitting while maintaining computational tractability. Climate modeling. Simulating our planet's future. Global climate simulations require enormous computational resources, making algorithmic efficiency essential for producing reliable projections. Scientists rely on sophisticated numerical methods to model complex atmospheric phenomena accurately. Finite element method implementations have been optimized extensively to balance precision with computational feasibility. Parallel processing techniques distribute workloads across supercomputers, enabling simulations that capture intricate weather pattern dynamics. Recent advances include adaptive mesh refinement algorithms that dynamically adjust resolution based on regional significance. This reduces overall computational load without sacrificing accuracy in areas requiring higher fidelity modeling. Data assimilation techniques integrate observational data seamlessly into simulation models. These algorithms continuously update forecasts with new measurements, improving prediction reliability for policymakers and researchers alike. Game development, crafting immersive experiences in the gaming industry. Algorithmic efficiency determines not just performance but also the quality of player experiences. Physics engines, AI routines, and rendering pipelines all depend critically on well-designed algorithms. Collision detection systems in first-person shooters must operate in real time with thousands of objects simultaneously. Spatial partitioning algorithms organize scene geometry hierarchically, drastically reducing the number of pairwise comparisons needed for collision checks. Pathfinding for non-player characters, NPCs, utilizes modified A** algorithms with heuristic functions tuned specifically for game environments. These optimizations ensure responsive AI behavior without overwhelming CPU resources. Rendering engines implement ray tracing acceleration structures that exploit geometric properties to avoid unnecessary calculations. Techniques like bounding volume hierarchies make realistic lighting effects feasible within acceptable frame rate limits. Conclusion: from healthcare to finance, from entertainment to scientific research, algorithm efficiency shapes our digital world in profound ways. Understanding its nuances empowers developers to create systems that perform exceptionally under pressure while delivering value consistently. As you continue your journey through the realm of algorithms, remember that true mastery lies not just in knowing the theory but in applying it creatively to solve real problems. Keep questioning assumptions, benchmark relentlessly, and always seek opportunities for meaningful optimization in your projects.